Hi, it's June again here. I know it's been a while. First off, I'd like to thank those who subscribed after my first few videos. Now, I did mention 6 months ago that I got a Supermicro motherboard. It's this one. It's a dual socket Xeon motherboard. Now, I only got this for $150 brand new. I know these days they cost around $500 used and around $1,000 brand new. Now, it's kind of a bit weird because this whole setup over here, it just cost me around a little bit over $1,000. And these days, they're just the cost of the motherboard. I could count myself pretty lucky because back in September, I already got all of my parts before everything skyrocketed. Now, I've got here two 6154 Xeon Golds, 384 gigabytes of RAM, DDR4 ECC. Now, this project has been a bit of a roller coaster ride for me because back in December, the motherboard pretty much died. So it wouldn't post properly and there's no video out. On IPMI, I could see it's stuck on error 78. Finally, on February, I got my replacement motherboard. So today, we'll move this a little bit janky setup where I've just used an open mine rig to something much more proper. This is a Silverstone RM44 4U chassis. And I'll also give you a preview on how to run very large models in one GPU only, and they'll be using a hybrid inference using the CPU and the GPU. We'll run GLM 4.7, Minimax 2.5, Qwen 3.5. But before that, let's go when I first got the motherboard. Oh wow, it's a brand new Supermicro X11 motherboard in 2025. It's still sealed. This is a 2018 dual socket LGA 3647 motherboard. Even comes with an old school QA checklist with it. Today, we're gonna be installing two dual Xeon 6154 on the Supermicro X11 motherboard. And inside, it's still in the anti-static bag. When I first built this, I couldn't find a clear video on YouTube showing how to assemble the LGA 3647 mounting system properly. So I'm putting together a separate video that walks through the full installation step by step. If you're interested, consider subscribing and you'll get notified when I publish it. Next is the memory, 12 32GB DDR4 ECC sticks, so 384 gigabytes total. Back in September 2025, this was actually the most expensive part of the build, almost half the system. At that time, I already was complaining about paying $50 per stick. Turns out that was a good thing. These days, the same modules are often $200 to $300 if you can even find them. So this is the system today. It mainly runs as a Proxmox host for my home lab. Some of my VMs live here, including a few for the agents like OpenClaw, CloudCode, and Codex. But one of the more unusual things that I've been trying is running LLM inference on this machine. Back in October, I started experimenting with IK version of llama.cpp after watching a video of Level 1 Text. I'll link Level 1's video below. That's what really got me started with this hybrid CPU and GPU test. For this test, I picked three very large MOE models, GLM 4.7, Minimax 2.5, Qwen 3.5. As of early February 2026, both Minimax 2.5 and Qwen 3.5 are current models. GLM 4.7 came out late 2025. And to be clear, this is not really a model shootout. These models have different sizes, different routing behaviors, and different architecture choices. What I actually care about is what they can teach us about running 100 billion parameter class models in a pretty ordinary hardware. Also, I should be clear that what I meant by run, in this case, it means the model loads, generates tokens, and can complete a prompt. So run here does not mean production ready, and it definitely does not mean ideal for interactive chat. This is more like, can I make these giant models usable at all in a modest box like this? So with that caveat out of the way, let's get into the benchmark summary and look at what the hybrid inference is actually doing. This summary page was pulled together with the help of my benchmark bot, and honestly, that saved me a lot of time. A lot of this workflow is repetitive. Load the model, wait, change the flag, wait again, record the numbers, break something, fix it, repeat. It was messy at first, but once I've turned the workflow into agent skills and build scripts around the repetitive parts,
This became pretty solid use case for local agents helping with benchmarks. Now, there's a lot going in this table, so let's simplify the goal first. With hybrid inference, the whole game is trying to keep both the CPU and GPU useful and busy at the same time. If the model doesn't fit well to VRAM, you either hit a out-of-memory error or you offload too much to the CPU and the GPU ends up barely doing anything. So you're always trying to find a balance. I still started with the usual constraint. Does this model fit the system RAM? Does it fit the VRAM? Which quantization is realistic? In very simplified terms, quantization means storing model weights in smaller, lower precision formats so the model takes less memory. If you want a deeper explainer in quantization, I'll link Julia's video below. I tried multiple quants early on, but for this comparison, I settled on Q4 across all three models, because that was the most consistent way to compare them in this hardware. These are the common flags that I ended up using across all three models. One important flag is the thread count. I set it to the number of physical cores rather than the hyperthreads. In these machines, that means 36 physical cores across the two CPUs. And this is where it gets interesting. Even with the same general strategy, each model wanted a different split between CPU and GPU. For GLM, I had to explicitly push 19 MOE layers into the CPU and cap the GPU at 75 layers. If I go beyond that, the 3060's 12GB VRAM becomes the limit. On this visualization, you can see the extra layers are loaded in the system RAM instead. And for those 19 CPU layers, both the layers itself and the experts are computed on the CPU, which is why it takes a performance hit. For Minimax, the approach was the opposite. There, I limited the CPU side into just 60 layers. Then I've used llama.cpp to push some of the layers into the GPU. So these 66 GPU layers are really 63 core layers and plus 3 expert layers. And in the diagram, you can see the 3 expert layers sitting on the GPU. Qwen needed a different trick again. There, I used tensor override to force the experts into the CPU, and then cap the GPU at 61 layers. With Qwen, the split is much cleaner. The core layers are on the GPU, while all the experts are handled by the CPU. Now, if you look at the figures, a few things stand out. First, none of the runs really actually saturated the GPU. GPU utilization is actually just around 13 to 32% on the average. Its peak utilization is actually pretty low. So even in a modest 3060, it's not even the bottleneck. The bottleneck is in the CPU side. Even when the CPUs are heavily loaded, I suspect the real limit is in the memory bandwidth, and maybe to some extent the cost of moving data around the system. These models are really huge, and once a lot of data are in the system RAM, you're asking for the CPU and memory subsystem to move a lot of data constantly. And in my case, it's probably worse because it's a dual socket system. This means NUMA effects, cross-socket traffic, and there's more chances of memory locality to hurt the performance. What's especially notable is Qwen. It's the largest module on paper at 397 billion parameters, but it only has 17 billion parameters active at the time, and that really shows up in the numbers. Even with a total number that's bigger, both prompt processing and generation are better than GLM. That makes sense, because Qwen only has 17 billion parameters active, compared to roughly 30 billion for GLM. So in the end, the build happened for one very simple reason. The motherboard was just too cheap, and my wife agreed with the purchase. I didn't have a planned use case in mind. I just bought it because it was only $150 and figured I'd learn something. And that part definitely worked. This machine taught me a lot about NUMA, Proxmox, VM migration, GPU passthroughs, and passing hardware on both VMs and LXCs. It also turned out to be surprisingly useful. I even used the VMs from this box in a CTF, where my bots managed to take the #1 spot. The organizer knew that I was using bots, so the points didn't count, but the results were still impressive. On the AI side, hybrid inference sent me much deeper than I expected. I learned a lot more about MOE architecture. At this point, I think the 3060 has done its job. It's useful for showing the constraints. But 12 gigabytes of VRAM isn't enough for a larger context that I want to try next. So the next step is to test one of my 3090s. I'm also considering a used V100 32 gigabytes. I want to see if I could get a usable hybrid inference with more VRAM, whether I could get a practical context window size. Despite the slow speed, this will be good enough for background agents. And if you've tried hybrid inference yourself, I'd like to hear how it went, because this is definitely harder than using Apple Silicon and unified memory, or just throwing the multiple NVIDIA GPUs at the larger models, just like what I did in my first build. I still owe an update on my first build, especially since I picked up a 5090 just before Christmas. I'll keep on trying to get more videos out. Thanks for watching, and if you want to follow the next round of testing, consider subscribing.